Chapter 1, the Introduction. What is geology? Geology is a science that pursues an understanding of the planet Earth. Physical geography is one major sub-area of geology. It examines the Earth materials and seeks to understand the many processes that operate on our planet. The other major sub-area of geology we're going to look at is historical geology. Historical geology seeks to understanding the origin of the Earth and its development through time. Geology, people, and the environment. Many important relationships exist between people and the natural environment. We have more people now living in cities than in rural areas, and that adds additional challenges. Populations are affected by geologic hazards and rely on natural resources. The natural resources may not be close on hand in the cities, and geologic hazards may impact cities. Geologic hazards are natural processes that adversely affect people. Natural resources addressed by geology include water, soil, metallic and non-metallic minerals, and energy. The Earth has been a focus of study for centuries. Catastrophism is a paradigm, an older paradigm or school of thought in geology, where it was believed that the Earth has been affected in the past by sudden, short-lived, violent events, possibly worldwide in scope. And these events carved out our current landscape. Okay. Now, our modern geology looks more at uniformitarianism as its paradigm or school of thought, which believes that the physical, chemical, and biological laws that operate today have operated throughout geologic past. And most geologic events or processes take a very long time to happen. So the idea is that the same amount of time they take to happen today, they took before. That doesn't mean there can't be a catastrophic event that changes some of the landscape. The difference is catastrophism believe there could be events that could have changed a major portion or even worldwide. Now, the magnitude of geologic time involves millions and billions of years. Okay, the Earth is 4.6 billions of years old. So the geologic time scale scans a very large range of time. So it's important to understand that those processes that occur over time are extremely gradual. Okay, so here's just a quick look at the geologic time scale. We'll be looking at this later chapter. But this geologic time scale, each one of these blocks has millions of years of time in them. Okay, so it goes back way far back, about 4.6 billion years. Okay, in order to do our study of geology, we use processes of scientific inquiry that are used in all scientific fields. Okay, so scientific inquiry. Science assumes that the natural world is consistent and predictable. The goal of science is to discover patterns in nature and use that knowledge to make predictions. Scientists collect data through observation and measurements. Okay, so once you've taken your measurements and observations, you'll make hypotheses or tentative explanations of what it is you've observed. And then you want to do experiments to test those ideas, those hypotheses. And a hypothesis has been well tested, has never failed, and scientists around the world agree that this hypothesis is really true. Then it becomes a theory. So scientific methods involve gathering facts through observations, formation of hypotheses and theories, communicating the findings, and then allowing others to test. Now, there's no fixed path that scientists follow that leads to scientific knowledge, but most scientific inquiries include those steps. Okay. Now, Earth is a planet that is small and self-contained, or relatively small and self-contained. There are larger planets and there are smaller planets. Now, at Earth, we look at Earth as a system that helps us break down the different processes we're going to be studying. So the four major spheres we're going to look at are the hydrosphere, and the atmosphere, the biosphere, and the geosphere. Okay. Here's a picture of the Earth taken from Apollo 17 back in 1972. What's key here is that we're able to study the Earth as a whole now. We can take pictures, we can gather data at a global scale. And we now have the computers to be able to process that data. So it's been quite a scientific revolution of data and information that's occurred since pretty much since the 60s or even the 50s. So Earth is a very dynamic planet with many interacting parts or spheres. Okay, so Earth system science aims to study Earth as a system composed of numerous interacting parts or subsystems. This employs an interdisciplinary approach to solve the global environmental problems. It means scientists from different fields need to work together. Biologists need to work with chemists, work with physicists to work with geologists, and work with climatologists in order to solve our current problems and issues. Okay, major cycles that we have in the Earth system. One is the hydrologic cycle. It's processing of water through the system. Also the rock cycle. Now, an interface is a boundary where different parts of the system come into contact or interact. The hydrologic cycle and the rock cycle interact in areas where there are glaciers. Okay? Glaciers are made of ice. They're part of the hydrologic cycle. But they also do erosion and transportation of sediment. And so that's part of the rock cycle. Okay, so here is a diagram of the hydrologic cycle and the rock cycle interface from a different perspective. So here we have, let's say we have a body of water and we get solar energy, okay, which is going to cause some of that water to evaporate. And then as it rises up high enough, that cools, that water condenses and forms clouds. And eventually there'll be so much moisture in the air and temperature may cool, so precipitation or rainfall will start to occur. That water will collect in stream valleys and flow down into rivers and back on out to sea. Okay, so the interface between this cycle and the rock cycle, while weathering, water and chemical interaction with the rocks is going to cause weathering to break them apart. Okay. Now those pieces are going to end up in that stream, and those sediments are going to travel downstream in suspension or bouncing along the bed, will be transported in the stream, and eventually the bits and pieces get settled into this lake or sea. And eventually those sediments are going to be compacted, and groundwater with mineral matter in solutions going to seep in and solidify, and we're going to end up going from breaking down these rocks to making a brand new sedimentary rock over here. Okay. So this Earth system is powered by the sun. It drives external processes, and these processes occur in the atmosphere and the hydrosphere and on Earth's surface. Earth system is also powered by heat from Earth's interior. This is remnant heat from the formation of the Earth. Earth and the other planets formed essentially at the same time out of the same material as the Sun. The nebular theory is the theory that proposes how our solar system formed, and proposes that bodies of our solar system evolved from an enormous rotating cloud called the solar nebula. Okay, solar nebula consisted of hydrogen and helium in addition to microscopic dust grains. A disturbance caused that solar nebula to slowly contract and rotate. The solar nebula assumed a flat disk shape with a protosun at the center as material gravitated to the center and eventually formed its own gravity. Okay, so it just started spinning faster and thinned out. And the materials in that nebula are sorted out by density. Okay, so the heavier particles were in the center, forming the sun, and each band of particles going out is going to be lighter and lighter. Now the inner bands began to form with metallic and rocky substances, so the more denser substances, so formed Mercury, Venus, Earth, and Mars. The larger outer planets formed from fragments of ices, okay, lighter materials, so water ice, carbon dioxide ice, and other ice, maybe methane ice. Okay. So here's a diagram of the nebular theory. So we had this nebula, rotating nebula, slowly fans out into a disk with a protosun in the center. Materials start differentiating by density, heavier materials to the inside, lighter to the outside. And eventually these particles in each band start colliding and aggregating to form planets. So we end up with our Sun, Mercury, Venus, Earth, Mars, the asteroid belt, well, yeah, Earth, asteroid belt, and then Mars, and then Saturn. Okay, so formation of Earth's layered structure. Well, the metals sank to the center, molten rock rose to produce a primitive crust. Chemical segregation established the three basic divisions of Earth's interior. A primitive atmosphere evolved from gases from Earth's interior, so water vapors and carbon dioxide. The earliest primitive crust was lost to erosion and geologic processes. Earth is divided into three major layers by composition. So the crust, which is Earth's thin, rocky outer skin, is divided into the continental and oceanic crust. Oceanic crust is approximately 7 kilometers thick and is composed of basalt. Continental crust is 35 to 70 kilometers thick and composed primarily of granodiorite. The mantle is approximately 2,900 kilometers thick and is composed of peridotite. The core is composed of iron-nickel alloy. Additionally, the Earth can be divided into different zones based on physical properties. So a lithosphere is a rigid outer shell of the Earth. It consists of the crust and the upper mantle. The asthenosphere is a soft, weaker layer below the lithosphere, and then there's a transition zone, a zone marked by a sharp increase in density that's below the asthenosphere. Then below that transition zone is a lower mantle. It's a zone of strong, very hot rocks subjected to gradual flow below the transition zone. The outer core is a liquid outer layer of the core, and the inner core is a solid inner layer of the core. So here's our diagram for all this. So we have our three major divisions. We have our crust, we have our mantle, a very thin crust, a mantle, and our core. Then by physical properties, we have our lithosphere, which is the crust and the upper part of the mantle. Then we have this transition zone. Below it we have our lower mantle, and then our outer core that's liquid, and then our solid inner core. Earth's surface is divided into continents and ocean basins. The difference between these two areas is the relative levels. The elevation difference is a result of differences between density and thickness. The continents are relatively flat plateaus, approximately 0.8 kilometers above sea level, composed of granitic rocks. The average depth of the oceans, composed of basaltic rock, is 3.8 kilometers below sea level. Features of the continents include mountain belts, cratons, shields, and stable platforms. Mountain belts are the most prominent features of the continents. Cratons are the stable interior of the continents. Shields are expansive, flat regions of deformed crystalline rocks in the cratons. Stable platforms are the flat portions of the cratons covered with a very thin veneer of sedimentary rock. So here's a map of some of this. So here, these yellow areas are young mountain belts. And these mountains are still growing. So here are Himalayas, our Alps, our Andes, are the North American Cordillera, which includes the Cascades. Let's see. The dark purple are our old mountains, the Appalachian Mountains, the Caledonian Belt. Okay. Then the shields, here's the Canadian Shield, the Greenland Shield, these are the stable parts of our continents, Brazilian Shield, and then the gray are stable platforms. Okay, also this is the shields that are covered with sedimentary rock. You notice that the yellow mountains are they're taller, they're more rugged looking. Okay, they're less worn down, less weathered. The older mountains, they're lower, they're more worn down. Okay. Now, the features of the ocean floor include continental margins, deep ocean basins, and ocean ridges. The continental margins are the portion of the seafloor adjacent to major land masses. The continental shelf is a gently sloping region of continental crust extending from the shore. The continental slope is a relatively steep drop-off that extends from the continental shelf to the deep ocean floor, and the continental rise consists of a thick wedge of sediment that move downward from the continental shelf and slope to accumulate on the seafloor. Then you have your deep ocean basins. These are portions of the seafloor between the continental margins and the ocean ridges. The abyssal plain is a flat feature of the deep ocean basin. Deep ocean trenches are deep and relatively narrow depressions that make up only a small portion of the ocean floor. And seamounts and guyutes are small volcanic structures that dot the ocean floor. The oceanic ridges are the most prominent features on the ocean floor and composed of igneous rock that has been fractured and uplifted. So rocks in the rock cycle. Basic rock types. We have igneous rocks. These are formed by the cooling and solidification of magma or molten rock. Examples are granite and basalt. Sedimentary rocks accumulate in layers of the Earth's surface. Sediments are derived from weathering of pre-existing rocks. Examples are sandstone and limestone. Now, metamorphic rocks are formed by changing pre-existing igneous, sedimentary, or other metamorphic rocks. Driving forces to cause this are heat and pressure. Examples are gneiss and marble. So here's an example of a granite. You see here's a nice chunk of granite. You see dark and light grains. This mountain here, this is in the Yosemite National Park. This is this big chunk of granite. Here's an example of sandstone. It's a sedimentary rock formed of fine sand grains. This rock here is a nice body of sandstone. It's in Zion National Park in Utah. Okay. So the rock cycle, it's a loop that involves the processes where one rock changes to another. Actually, it looks more like a wagon wheel because even though you think of it as a cycle that goes around the outside, there are a lot of shortcuts where any kind of rock can become a metamorphic rock. We'll see in the illustration. But it illustrates the processes and paths that Earth's materials change both on the surface and inside the Earth. So here's our rock cycle. Here we have some molten magma. Okay, as it cools, it starts to crystallize and form igneous rocks, which then later can be weathered and transported as sediments, which then get deposited and later get lithified, compacted, and cemented together to form sedimentary rock, which then can be buried and under heat and pressure turn into metamorphic rock, which then later on can be melted. Now here's the shortcuts. Okay, igneous rock can be metamorphosed. Metamorphic rock can be weathered and deposited and later turned into sandstone. So there's a lot of different paths the rock cycle can take.